Hello everyone, today let's take a look at a good question right here, QP 145. So if I have 8 cards that are drawn at random without replacement from a standard deck of 52 and we let X be the number of spades in the hand, what is the variance of X? So X is the number of spades in your hand. We're trying to find the variance of X, which is just equal to the expected value of basically X minus the expected value of X all squared right here. Or you could write this as basically the expected value of X squared minus the expected value of X all squared, like so. In either case, if you wanted to calculate these straight up, it's pretty much going to be almost impossible. These are going to be huge hypergeometric sums that you're taking with huge numbers. But again, you notice in this question, we have X, which is counting the number of basically identical things in a hand. So that just immediately tells us that we're going to be able to use linearity here. So for the 8 cards that I'm dealt, I could get a spade, and then maybe I get a heart, and then maybe I get another spade, maybe I get a diamond, maybe I get a heart, maybe I get a club, and then etc. Something like this, right? Some sequence. And we're just counting the number of spades. That's what X is doing. So we can define our indicators. Basically, I'm going to find I sub 1 to be for the first card that we're dealt. I'm going to say it's equal to 1 if it's a spade, and it's equal to 0 if it's not a spade. And then for my second card, I'm going to define another indicator. So I sub 2 is also going to be equal to 1 if it's a spade, and 0 if it's not a spade. And same with I sub 3 for this one right here. Same with all of my cards. So I sub k, I'll say, is equal to 1 if it's a spade, and 0 if it's not. So we can just express X right here. X is just going to be the sum of basically all of these indicators I sub k, where k is going from 1 to 8, 1 for all 8 of our cards. So to use this sequence right here as an example, this is how it would work. Well, we have a 1, and then we have a 0, and then we have a 1, and then we have a 0, and then we have a 0, 0, 1, 0. When we sum these all up, we get 3, which is the number of spades in our hand, obviously, right? So that's why we can express X that way. So first of all, before you calculate the variance, let's first calculate the expected value of X, which is just going to be the expected value of basically the sum from I equals 1 to 8 of basically I sub k. And even though these indicators right here are not basically independent, because if I draw a spade on my first card, then I'm going to be less likely on my second card, right? It's not going to stay a constant distribution. That's because I'm sampling without replacement. Even though that's true, linearity of expectation still works, right? I can just take this as the sum from I equals 1 to 8 of the expected value of I sub k. That's the whole reason you use linearity of expectation. What makes it so useful is that property right there. Also, obviously, the expected value of an indicator is just equal to the probability that it's equal to 1, so the probability that it is a spade. So now I can replace that in here. This is just going to be the probability that I sub k is equal to 1. Well, all of these indicators are going to have the exact same probability, because if we're just looking at card number 2 in a vacuum, basically, right? Well, the probability that it is a spade is going to be exactly the same as if we were looking at card 3 in a vacuum and we were trying to find the probability that it was a spade, right? So the probability that the third card in our deck is going to be a spade, well, what is that? Well, there's 13 spades in the deck and we have 52 total cards, right? So there's a 13 out of 52 chance that each one of these is going to be a spade, right? So this is just equal to 13 out of 52 for all k, right? So this is just going to be equal to 8 times 13 divided by 52. So that's just 8 times 1/4, which is going to be equal to 2. So that is the expected value of X. Also note that we could have defined our indicators differently, right? We could have had I equals 1 to 13 representing all of our 13 spades, where we have the probability that I sub j, I'll say, let's have a j here, right? The probability that I sub j is equal to 1 is going to be the probability that a spade gets chosen as one of our 8 cards. And again, now I'm just realizing that this should have been a k up here, obviously, right? I keep on doing that. K right here, k, k. But anyways, down here, we're summing up over our 13 spades, and we're calculating the probability that each of those spades gets chosen as one of our 8 cards in a vacuum independently. Again, we could have used linearity of expectation like this, where this probability here would just basically be 51 choose 7 out of 52 choose 8. That's because, for instance, if we're dealing with, like, let's say the jack of spades, well, then the jack of spades, we're choosing that, and then we're choosing 7 of our remaining cards to be in this group of 8, divided by basically the total number of ways that we could choose a group of 8. So we sum this up, we just get 13 times, well, this right here is just going to be 8 on 52. So again, we're going to get the exact same answer of 2. So you could have defined your indicators like this, but we did it like this because this one's going to be more simple. So we'll just stick to this way up top. But however, the variance is not as simple as basically the expected value. The variance of X is going to be a little bit more complicated. Let's do that down here. It's not going to be so simple because we basically just have these squared terms up here, and squaring a sum is going to be a little bit more complicated, right? We're still going to use our indicators and it's going to make it a lot easier, but it's just going to be a little bit more complicated. So now I'm taking the variance of the sum when I use my indicators, the variance of the sum from I, let's do it right this time actually, k equals 1 to 8 of basically I sub k. Now the variance of a sum is only going to be equal to the sum of the variances when these actual indicators are independent, right? Unlike expectation, right? It's only going to be true when these are independent, and in this case they're not, they're dependent. Again, that's because if I draw a spade on my first card, we're drawing without replacement, so the probability of me drawing a spade on my next card is not going to be the same, right? So there are two ways to solve this. I'm going to do it the first way, which is what we talked about in QP41. It's basically the linearity of variance. When they're dependent, it's just going to be basically the sum from k equals 1 to 8 of basically the variance of I sub k. When they're dependent, like we talked about in QP41, we're going to have to add on basically the sums of all the pairwise covariances, right? So j equals 1 to 8 and I equals 1 to 8 of the covariance of I sub I with I sub j. But this second sum, the inner sum, is also under the condition that j is not equal to I, because basically the covariance when j is equal to I is just going to be the variance, which we've already calculated over here, right? This is all what we talked about in QP41. And then again, in this double sum right here, we're calculating the covariance of I sub 1 comma I sub 2. And then later on in the sum, we're going to calculate the covariance of I sub 2 comma I sub 1. So these are going to be the exact same thing as well. So we can basically rewrite this as just a singular sum. So because we're double counting basically every ordered pair, we can just say 2 times all of the ordered pairs. So 1 less than or equal to I less than j, right, all the way up to 8. But again, we know the covariance of I sub I and I sub j. We can just express that basically as the expected value of I sub I times I sub j minus the expected value of I sub I times the expected value of I sub j, like this. But also the expected value of any of our indicators, we already calculated that, it's going to be 1/4. So this right here is just going to be 1/4 times 1/4, so 1/16. So now what is this right here? Remember, I sub I and I sub j are not independent, so we can't just multiply their expected values. Well, in this expected value, we're multiplying two indicators that could each either be 1 or 0. So this right here, when they're multiplied, is only going to be 1 when both of them are 1, right? Because if one is 1 and the other is 0, then it's going to be 0, right? And if they're both 0, then obviously it's going to be 0. So now what's the probability of these when they're not equal to each other, right? So the probability of this one, let's say we just choose two of our, basically our card positions. And the probability that they're both spades is going to be the probability that our first one is a spade with probability 13 out of 52. So 1/4, it's just going to be 1/4. And then once we've chosen that, we still have to choose a spade for our other card, right? And now there's only going to be 12 spades left in the deck out of 51, right? So we have a 12 out of 51 chance of choosing another spade. So now if we cancel 4 on top and bottom, we just get 3 out of 51, which is equal to 1 on 17. So that's the probability that basically the multiplication of these is equal to 1. And it's 0 in all other cases. So the expected value of this is just going to be this probability right here. It's just going to be 1 on 17. So we have 1 on 17 minus 1 on 16 in this sum. So 17 times 16 is 272. So this is going to be negative 1 on 272 right here. And we're summing that up over all the possible combos of I and j such that they're less than 8, right? And they're not equal, right? So I know it's confusing, but this sum right here is just meant to represent basically like the covariance of I sub I. And then we have basically that with I sub j, where I and j are not equal, and we're summing up over every single ordered pair, right? So how many pairs are there of I and j? Well, we have 8 total cards, right? So it's just going to be 8 choose 2. Now 8 choose 2 is 8 times 7 on 2, so 56 on 2, so that's going to be 28 right here. So we're summing up this 28 different times. So this is 28 times basically negative 1 on 272, and then we're also multiplying that by 2, right? So this is just going to be 56 right here times negative 1 on 272. So this term right here is going to simplify down. Basically, when you simplify, it's going to go down to negative 7 on 34. Okay, now the variance of an indicator is going to be a little bit easier, right? Remember in QP91, we derived the variance of an indicator is just going to be equal to p times 1 minus p, where p is the probability that the indicator is equal to 1. So in our case, the probability that one of our indicators was equal to 1 was just going to be 13 on 52, or 1/4. So right here, we just have 1/4 times basically 1 minus 1/4, so 3/4, and that's just going to be equal to 3 on 16. Okay, so the variance of our indicator is 3 on 16. We're summing that up 8 different times. So we're going to have 8 times 3 on 16 right here. So 24 on 16. We're subtracting off 7 on 34. Okay, so now 24 on 16, that's just going to be 3 on 2. We're subtracting off 7 on 34. So that's going to basically be, we can multiply to get a common denominator. We're going to get 34 on the bottom when we multiply divide top and bottom by 17, and we get 51 on top right here. And then we're going to basically just have 44 on 34. So that right there is just going to simplify down to 22 on 17 in lowest form, and that's our final answer, the variance of the number of spades in our first 8 cards. The other probably simpler way to solve this would just be to calculate it using this formula right here, where we just have to find the second moment, so the expected value of x squared. Well, we can just write that as the expected value of the sum of all the indicators squared, so that right here is just basically going to be equal to I1 plus I2 plus ... plus I basically sub 8, and this is going to be raised to the power of 2. When you expand this out, a little binomial theorem action, right, we're going to have I1 squared, we're going to have I2 squared, right, and then we're going to have 2 times basically all of the pairwise things, right, so we're going to have 2 times I1 times I2, we're going to have 2 times I1 times I3, etc., right? So that's why we can write it as the sum of 2 terms as we did previously, right? We have the sum from k equals 1 to 8 of basically, what do we have, I sub k squared, and then we need to add on all of these terms, right, that have a coefficient of 2 out in front, and that's when I and j are not equal. So to add on all of these terms, we can write this as basically 2 times the sum from 1 less than or equal to I, which is less than j, so all the ordered pairs, right, up to 8, and then we have I sub j times I sub I. Also, whoops, that's what this right here is equal to, and we're taking the expected value of that, so we know by linearity of expectation, since we're just doing a bunch of sums here, we can pull the expectation inside. That's what makes linearity so nice, right? I sub k, and then that's going to be squared actually, so like that, and then we have these over here, the expected value of this. Now we've already calculated this before, the expected value of I sub j times I sub I, when they're both different. Well, we know that I sub j is either equal to 1 or it's equal to 0, and same with I sub I. So this is only going to be equal to 1 when they're both equal to 1. In any other case, it's not. So this expected value right here is just equal to the probability that I sub j and I sub I are both equal to 1. So I sub j equals 1 and I sub I equals 1. And this is for, again, when I and j are not equal. So this probability right here is like we're basically looking at 2 cards. So what's the probability that we get 2 spades? Well, for the first one, it's going to be 1/4, right? 13 out of 52. And then for the second one, we're going to have a spade removed. So it's just going to basically be, well, 12 out of 51. So that's just going to be equal to 1 on 17. So the expected value of I sub j times I sub I is just going to basically be 1 on 17. And we're summing up here over all the ordered pairs of our indicators. So how many are there of those? Well, we just have 8 choose 2, right? That's the number of ordered pairs, which is just going to be 28. So we're summing up 1 on 17 28 times, and then we're multiplying that by 2. So that's just going to be 28 on 17 times 2, which is just going to be 56 on 17. Okay, so now for the expected value of an indicator squared. Well, an indicator can only take values 1 or 0, right? And when you square 1, you get 1, and when you square 0, you get 0. So this is just going to be the exact same thing as the expected value of any of our indicators, which we know are all equal to 1/4 from previous parts. So this was a plus, not a minus. I don't know how that went away, but basically we are summing up here 1/4 8 times. So that's just going to be 8 on 4, which is equal to 2. So now we're adding 2 plus 56 on 17, which is just 34 on 17 plus 56 on 17. So that's 90 on 17. That's the second moment of basically x. So now for the variance, we still need to calculate this up here, which is just going to be the expected value of x squared, which we got was 90 on 17, minus the expected value of x all squared, which we calculated at the very beginning of the video, right? Remember, we got 2, so we have 2 squared here, so that's just equal to 4. Now, 4 is just the same thing as 68 on 17, so when we subtract these here, we get 22 on 17, the same thing that we got back here. So you can do this either way, right? You can do that either way. So this is not the answer to this question. This right here is the expected value of x, it's 2, and this right here is the variance, 22 on 17. Our second moment was basically 90 on 17, not that it matters, but this right here was our variance, right? That's what we were originally trying to solve.